this. And we are now going to use vectors for all the quantities that are directional that have to do with kinematics. So that means mainly position is a vector, velocity is a vector, and acceleration is a vector. And I have to give definitions to you of what all those things mean as vectors. We're only used to dealing with them so far as signed numbers. So I'm going to start with position, and I'm sort of going to go through the same process that I went through in one-dimensional kinematics. So first, the position vector. So in 1D, I drew a train track, and I drew a train, and it was 1D motion, so the train was confined to the train track. At any point, it could only go one way or the other way. We called one of those directions positive and one negative. We chose a 0 position, and that let us assign a number to it. So, okay, so now here's the train. But now it's not confined to a track, so it has wings. So now that it can move in 2 dimensions, it can go this way or that way, this way or that way, or anything in between. So there's infinitely many directions that it can choose. We're still doing particle kinematics, excuse me. And that means that we have to define the location of this train at a single point. So I'm going to choose the center of mass. Okay, so what does it take for us to assign a vector to this point, this location? So the train's at a physical location. What does it take to assign a vector to it? In 1 dimension, we had to choose the 0 position in the positive direction. In 2 dimensions, we're going to do something analogous to that. The 2-dimensional version of a 0 position in a positive direction is, first of all, we have to choose an origin. I'm going to call that scripty O, origin. And then we have to choose an orientation of a coordinate system. So for now, I'm going to choose the one that you're most used to, but that won't always be the case. And so the 0 position now is the origin location. The positive direction in 1 dimension now translates into the coordinate system axis directions, how the coordinate system is oriented. And once you choose those, you can draw a vector that goes from the origin to the point that you care about, and this is the position vector. Position vector. And one thing to notice about this is that the position vector is, you can think of that position vector as being the exact same thing as giving the coordinates of the object in the coordinate system we just defined. So finding the position vector means finding the coordinates of the object at an instant. The units are the same as they were in 1D. So units per position. It always has to have units of length. So depending on what system of units you're using, that could be feet, miles. More often, we're going to use SI units, so it's going to be meters. And most of the time, so this is a drawing of the position vector, but if you knew something about the length, like how far that was from the origin, and you knew something about an angle between the coordinate x-axis and that vector, you could use that to calculate the components of the vector, and then you could do math with it. By the way, we have, and actually we're going to keep doing this, we put a lot of emphasis on position versus time graphs. In 2 dimensions, we're not going to use position versus time graphs so much. Remember that now a position vector has 2 components, an x component and a y component. And if you wanted to graph position versus time in 2 dimensions, the clearest way to do that would be to plot separate x position versus time and y position versus time graphs. And so it's not quite as concise a description of what's happening. But you could do that. Let me do a couple examples. So if you have a coordinate system like this, and most often, I wrecked my voice trying to get you guys to shut up at the beginning. No thanks. Would I? No. My voice sounds really cool now. It's just not very loud. Okay, so let's say that you have an object located at this point here, and you know that the distance is 5 meters. What's the position vector at that point? In components. Yep, so that would be, you can think of that as just calculating the coordinates at that point. So that's 0 in the x direction, and then 5 in the positive y direction. And so whenever the object is on any of these 4 axes, it's really easy to come up with the position vector. So if it's 5 meters in this direction along the x-axis, the position vector will be 5, 0, 0, 5, negative 5, 0, and 0, negative 5. Okay, and for position, that's going to be the most common thing that we have to do is just come up with vector components for objects that are along these axes. It's not as common with a position that you're going to know something about an angle and a distance and calculate the components, although you could do that if that was given. Okay, so next is the velocity vector. And the mathematical definition of the velocity vector works exactly like in one dimension. Remember, we defined an average velocity. And this time the average velocity is going to be a vector. And it's equal to the position at the later instant. And now that position is a vector. Minus the position at the earlier instant. And that position's a vector. Divided by T2 over T1. So that definition looks exactly the same, except vector quantities are vector quantities now. And then in order to define the instantaneous velocity, as you pinch these values of T1 and T2 closer and closer to your desired value T, that average velocity vector approaches the instantaneous velocity vector at the time T. Okay, so that's defined the same way. You choose a T1 and a T2 on either side of the time you want, and little by little you pinch them closer together, and this as you get those T values closer to your T, that average velocity gets closer to the average velocity. And like before, we're not going to use that, but that's kind of like an intuitive definition. So this, like in 1D, we never really used that definition, except if you want to sort of understand where it comes from. We used other equations to come up with it, and that's the same thing we're going to do here. And just like in 1D, this is the only one we care about. So this is the important one to us, the instantaneous velocity. And so again, if I talk about the velocity vector and I don't say anything about average or instantaneous, I'm talking about instantaneous. If I ever want average velocity, I'll say that specifically. There's a couple of things to notice about the velocity vector. Oh, sorry, before I do that, let's do the units. And all the units are the same as they were in 1D. So the units for the velocity vector are always going to be length over time. And so if you're using SI units, meters per second. Okay, so notice, first of all, the velocity vector is always in the direction the object is moving. That was true in 1D too, except we only had two choices for the direction. Now we have infinitely many choices. So the direction of the velocity is the direction that the object is moving. At that instant. Yeah, all of these change with the coordinate system. The components do. And just like, so the components change, although you can think of the vector as being, well, Um, the vector itself doesn't really depend on the coordinate system. And that was the same as it was in 1D also. Like if a car is going this way, it doesn't matter whether positive is this way or positive is this way. The car is still going this way. And you can think of the vectors that way too. But when you start to put components to them, you need a coordinate system orientation, and that coordinate system determines what those components are. Yeah. Second, the magnitude of the velocity, the magnitude of the velocity vector v is the speed. So that was true in 1D also, like if we were given a speed, if we said something was going 10 meters per second to the, what side is that to you, right? Something's going 10 meters per second to the right, and say our positive direction was to the left, then for the velocity, we would say 10 meters per second negative because it's going in the negative direction. Now we'd say we have a vector whose length is equal to, or magnitude is equal to 10 meters per second, and we'd use the angle of its motion to come up with the components. And the third thing to notice, to keep in mind, is that velocity is the one where we're really often going to be given a magnitude and a direction, like an angle, and have to come up with the components from that. So we'll often need to calculate the velocity vector from its speed and angle. So for example, if an object is launched at 20 meters per second, at a speed of 20 meters per second, that means at, let's say, 30 degrees above the horizontal. And say we're using a coordinate system like this. Then you would, at that instant that it's launched, you would draw the velocity vector like this. It has a magnitude of 20. And it makes an angle of 30 degrees above the horizontal. You could think of this with the units. And so the velocity vector at that instant would be 20 times cosine of 30 degrees, 20 times the sine of 30 degrees. And that would be 17.3210 meters per second. And now that you've expressed that velocity in components, now we can add it easily. We can multiply it by numbers, and we're going to have to do all that stuff with constant acceleration equations. Any questions about that? Okay, one last thing that's going to be important here is in 1D, how did we specify when something was launched up into the air? How did we specify when it reached its highest point? the velocity was equal to 0. So now things can be launched. They can be launched like at an angle. They're not just going straight up and straight down. Okay. So, but like if you launch something this way, it's going to follow a path like this, reach a highest point, and then start coming down. So how do we specify the highest point in a projectile path in 2D? You know, your first thought might be the velocity vector is equal to 0. That's on the right track, but it'll actually, when it reaches its highest point, it'll still be moving horizontally. So in 2D, to specify the highest point, we say the y component of the velocity is equal to 0. Well, if we use this standard coordinate system. So I'm going to say for a coordinate system with the y-axis up, the highest point in a projectile motion is when the y component of the velocity is equal to 0. The x component won't be equal to 0. And here's a thought experiment to clarify that for you. So like imagine, so like a pro baseball player, an outfielder can throw a baseball like, you know, from the outfield wall home 400 feet or whatever. So imagine somebody does that. Can I draw this? I don't know. What leg would be back? This one. This would be forward. It looks like a gorilla, possibly. Okay, so this guy throws this baseball anyways. And it follows a parabolic path. Okay. He's wearing clothes. The highest point of the ball's path is here. Okay. So if the velocity was equal to 0 at the highest point, then at that instant, the ball is not moving at all. And so you would have no problem that's supposed to be you. It looks a little like you. Okay, that's supposed to be a person, maybe a small kid. But okay, so if the velocity vector was 0 at the highest point, and you could set up a ladder right where the ball is going to be at its highest point and put your head right where the ball is going to go, and the ball would come here and just nuzzle gently up against the back of your head. The velocity would reach 0 right there, and it would be at rest at that instant, and you wouldn't even feel it. But you know that this would be a really bad idea, you know? So this is what I want you to picture anytime you get close to saying velocity vector is equal to 0 at the ball's highest point. Velocity vector is not equal to 0. And then the last definition we need is for the acceleration vector. So remember that in 1D, and it's true here too, acceleration is a measure of how quickly the velocity is changing. So acceleration measures how quickly the velocity is changing. In 1D, well, so in parentheses here, that means that if the velocity isn't changing, so if the velocity doesn't change, the acceleration vector is 0. In 1D, any non-zero acceleration meant that the object was changing speeds. So the only thing that acceleration can do in 1D is make an object speed up or slow down. Now there's a new thing in 2D. This did not exist in 1D, but in 2D, non-zero acceleration can mean speeding up or slowing down. And or, this is the new thing, turning. You know, in 1D, there's no such thing as turning because your path is fixed. But now something can have a velocity this way and then start to do this. It's all of those velocity vectors are contained in 2D. So for example, this is a new thing. This couldn't happen in 1D, but you know, think about that astronaut training thing that they use to get astronauts used to high G forces. So they have this arm. The astronaut sits in a chair over here. That's how you know it's an astronaut. You don't really need a helmet for this experiment, but so you know what I'm talking about? This thing goes around like this. Okay, so so they do this to get astronauts used to really high accelerations. You know, you have to get your body used to dealing with high accelerations. And how does this produce high accelerations? I mean, it makes sense while this thing's speeding up. But actually, it only speeds up for a while, and then it's going at a constant speed. You know, the astronaut's going 20 or 30 meters per second steadily around this circle. But it's still causing big accelerations. And the reason it's causing big accelerations is because it's a really rapid change in direction. Even though the speed's constant, the astronaut's turning really quickly. And that change in direction is a change in velocity. The velocity vector is changing. The velocity vector is this way at that instant, and over here it's this way. And that rapid change in direction is an acceleration. So you can get really high G forces. And when you're at Valley Fair going over rides, a lot of those rides you're going at a constant speed. It's not the change in speed that you feel as an acceleration. You feel that acceleration because your direction is changing quickly. Or like if you're in a car, you go through a turn too quickly. It's the same thing. Your speed isn't really changing, but you're just changing direction fast enough that you feel the acceleration. Yep. Yes. Yes, exactly. Yep. By the way, just since you mentioned that, just getting ready for this. So centrifugal force is the more common force that that you sort of hear about in everyday language. That's not going to be a thing in this class. Maybe I'll sort of explain it as we go. We're going to deal with centripetal force. Sounds sort of similar, but it means something different. And they both kind of get at the same thing, but it's sort of approaching it from a different vantage point. Okay, so the mathematical definition of acceleration is the same as it was in 1D, except everything's a vector now. Well, velocity and acceleration are vectors. So the acceleration is equal to the velocity at the later time minus the velocity at the earlier time divided by the later time minus the earlier time. And again, we don't have to differentiate in this class between between average and instantaneous acceleration because we're only doing constant acceleration, so they mean the same thing. The units for acceleration are the same as they were in one dimension. So that's length over time squared. And that means that if you're using SI units, acceleration is meters per second. And for free fall problems, remember free fall and projectile motion are probably the most important application of the constant acceleration equations. If something's in free fall or projectile motion, if you choose a y-axis up, then the acceleration vector is known. And anytime something's in free fall or projectile motion, point in the direction of the acceleration vector. Yep. Down, right? If the y-axis is up, that's the negative y direction. And so the acceleration vector would be 0, negative 9.81 meters per second squared. And we're going to use that a lot. Okay, so now that we've defined all these vector quantities that are important for kinematics, we're going to start. I'm going to give you the constant acceleration equations for vectors for two-dimensional kinematics. And they're going to look a lot like the ones for 1D kinematics. And then I'm going to give you a set of steps for using those. So here are the constant acceleration equations for two-dimensional kinematics. And that's still, we're still only dealing with particles. Okay, so the first equation that we had in 1D said velocity final is equal to velocity initial plus a times time final. And that still holds in two dimensions, except we have to deal with components. So this is true for x components. And it's also true for y components. and everything on there has a subscript that tells you what component you're talking about, except time final. Why doesn't time final have it? Because time isn't a vector. Yep. Time means the same thing that it did in one dimension. It's just a number. It's always positive. So time isn't a vector. No, so if you're doing this and your y-axis is up, then ax is 0 and ay is negative 9.81. That's the vector notation. The x component is that, and that's the y component. And then the second equation in 1D said PF is equal to PI plus VI PF plus 1/2 A PF squared. And that's true for the x components. And it's also true for the y components. And then the last equation said 2A times the quantity PF minus PI is equal to VF squared minus VI squared. And that one's true for the x components. And it's also true for the y components. So if you remember those equations from 1D, it's pretty easy to remember them for 2D. You just have to do twice as many of them and put the components on each one. Okay, and now I'm going to go through a general set. Yes? Like in the calculations? Okay, so yeah, that's a good question. So at this point, I don't care anymore about that. You can, for all the equations from now on, you can skip the units in the calculation. Just remember to put your units on your final answers. So I wanted you to do it at first to see how it works out, but now we're going to be sloppier with that. Any other questions? All right, so here is a general set of steps for using the constant acceleration equations in 2D. And these steps are going to follow really closely the steps in 1D. So, okay, what was the first step in 1D kinematics for using those equations? We had to choose 4 things. Yep, right. Time equals 0. Time final. Yep, right, good. So we had to choose those 4 things. And we still have to choose time equals 0 instant. and the time final instant. And then the other two are choosing a zero position in a positive direction. What do you think those are now in 2D? That's right. Yes, exactly. So we also have to choose the origin location and the axis orientation. Um, and a lot of times I'm just going to call these two things together, choose the coordinate system, but it's sort of two separate aspects of the coordinate system. So just keep in mind that that's all we're doing is the two-dimensional version of the stuff we had to choose in 1D. And then once we do that, what was the second step? Yeah, so we had to figure out, so determine what variables you know and what variables you want, or what variable you want. And in 1D, we went through the list of 7 variables that we had. Now we have a whole bunch. Not quite 14, just because time is, but yes, that's exactly the right way to think. So now we have time final, AX and AY. PI, X and Y. PF, X and Y. VI, X and Y. And VF, X and Y. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's a little more of a bookkeeping issue, but it's the same idea. We're just going to go through those one by one and figure out what we're trying to find and which ones we know. Then step 3, we're going to look for an equation out of the 6 possible constant acceleration equations. We used to only have 3, now we have 6. So look for an equation that has the variable you want and where all the other variables are known. If you can find that equation, you can use that to solve for the variable you want, and you're done. That was in 1D, that was almost always the case. There's sometimes cases where you have to find an intermediate variable. In 2D, it's more common that you're going to have to first go back and find an intermediate variable. So we called this step star before. So if you can't find an equation that works, look for an equation that'll let you solve for an intermediate variable. And this intermediate variable is almost always going to be time final. And then once you're done with that, once you've solved for time final, go back to step 2 and look for an equation that, now that you know a new variable, go back, include that in the stuff you know, and look for another equation. Okay, so why is it that time final is going to be so useful in two-dimensional kinematics as an intermediate variable? The reason is that notice that these x and y equations, and there's an x and y equation for every one of these equations that we had in one dimension. There's no crossover between variables from the x to the y's, except for time final. Okay, so that's the thing that makes time final really useful in 2 dimensions. It lets you use, like, say, I guess the most common one we're going to have is we're going to use a y equation to solve for time final, and then we can use that time final we solved for in the x equation. That's the only variable in all these 6 equations that crosses over from 2 dimensions. Okay. Any questions about that before I start doing example problems? Okay. So my first example is a Joe Mauer tribute question. I'm going to be pretty busy for the rest of class drawing this picture. Let's see. You guys drawing it? It's supposed to be like a glove. Okay. What number is he? 7? Okay. Okay, so let's say he's going to release the ball here. And then the ball is going to, go like this. And let's say that the ball, the instant it leaves his hand, it makes a 25-degree angle with the horizontal. And at the instant it's released, so let's say it's released at 40 meters per second, 25 degrees above horizontal. And we want to know how far will the ball travel horizontally before it hits the ground. So basically, like, how far does he throw it before it hits the ground? Yes, I need to give you that information. So let's say that this, height is 1.5 meters. And let's go through the steps. So the first step is we have to choose the origin location and the axis orientation. And we have to choose time equals 0 and time final. The stuff that went into choosing time equals 0 and time final in 1D is the same stuff that we use to make the decision now. So what do you think is going to be our time equals 0 instant? Yep, instant that the ball's released. And what about time final? Hits the ground. Yep, exactly. And then for the coordinate system, I'm going to put the origin in the place that I put it in almost every one of these problems, maybe every one. I'm going to put it on the ground right beneath where the thing is at time equals 0. So right here. So the origin location is going to be on the ground beneath the ball's location at time equals 0. And then the coordinate system, the axis direction, coordinate system orientation. I'm going to have the y-axis up, and I'm going to use that in every free fall problem too. And the x-axis horizontal in the direction of the ball's motion. Okay, so my y-axis is like this. My x-axis is like this. And now we can start to think about what we know about the variables. So here are the ones we know and the one that we want. So let's just go through that list of 13 in the same order that I did in one dimension. Do we know time final? Do we know like how long it takes a stopwatch, how long it would say it takes for the ball to leave his hand and hit the ground? No. If we can do this problem without knowing time final, we're fine with that. So for now, I'm going to leave that out. Do we know anything about the acceleration? Yes. What's the x component? 0. What's the y component? Yep, negative 9.81. Do we know anything about the initial position? Yeah, so remember that's the initial position vector is the coordinates of the ball at time equals 0. So we're looking for the coordinates of this red star. What's the x component? What's the x coordinate? So 1.5 would be the y component. X would be 0. So pix is 0. piy is 1.5. Do we know anything about the final position? Yeah, we know the height is 0. So pfy is 0. And what we're looking for is the x position when it hits the ground. So that's the one that we want, pfx. Any questions about that? Yes. Because our coordinate system is on the ground, and when the thing hits the ground, we know that its height is 0. Do we know anything about the initial velocity? Yes, that's where we're going to use this stuff. We're going to use the 25-degree angle and the 40 meters per second. So VIX, VIY, those are both going to come from, so the way to do that is like those vector homework problems. We have a vector, if we put its tail at the origin, we have a vector with a length of 40, and this angle is 25 degrees. So that initial velocity vector is 40 times cosine of 25 degrees, 40 times the sine of 25 degrees. And if your calculator's in degrees, if you get like the most common thing that goes wrong in calculating these, punching these into your calculator, is that your calculator's in radians. So let me know if yours is in radians and you can't figure out how to switch it. But if it's in degrees, for VIX, you would get 36.25. And for VIY, you would get 16.90. And then do we know anything about the final velocity? That's right. We can't say it's 0. There is something that you'll probably start to notice as you go through this, and that's that in free fall problems, the final x component of the velocity is always the same as the initial x component of the velocity. Okay, so yes, it turns out that the x component of the final velocity is going to be 36.25. But now that I've said all that, we're going to pretend like we don't know that. We're going to pretend that's something we have to calculate each time. If you do write that down in your column of things that you know, it will look sometimes like there's an equation that works when it turns out if you plug it in, all this stuff cancels out and you get a 0 equals 0 equation that doesn't help anything. So we're gonna treat it like we don't know anything about the final velocity. Okay, so here's the final state. We want to find PFX. We know all this stuff. So is there any one of those 6 equations that has PFX in it and everything else in it is known? Well, I think there are only 2 of those 6 equations that have PFX, so that narrows it down quite a bit right at the start. So the only candidates are this one and this one. And so now we want to look at those 2 equations and see if either one of them, see if the rest of the variables in either one of those are known. If you look at this one, we didn't know TF, so we can't use this one. And if you look at this one, we didn't know VFX, so we can't use this one. And now, that whole long thing I said, sort of for no reason, if you were listening to that, you say, wait a second, we do know this. Why don't we just use this one? Well, this is exactly the case where, so we'd say like, okay, this equation looks like it works, but if we plugged it in, this side would go away and it would give us nothing. So we wouldn't be able to calculate what we want because of the 0 acceleration of x. Okay, so nothing works. Okay, none of those equations work. No equations work. So now we have to go to step star. And what does step star say? Yeah, so let's instead go to our plan B and try to find an equation that lets us solve for TF. That's right. And it's because of it often works exactly like it's going to work in this one. We're going to be able to get TF from a Y equation and then plug it into an X equation. Okay, so now is there an equation that has TF and everything else in it is known? This one will work. PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. Yeah, we didn't know what it was for X, but now since we're looking for TF, we're not confined only to X equations anymore. So now we're going to use a Y equation to find TF. So this one says 0 is equal to 1.5 excuse me, plus VIY is 16.90 times TF plus 1/2 times negative 9.81 times TF squared. And I'm going to rewrite this as 0 is equal to negative 4.905 TF squared plus 16.90 TF plus 1.5. So can anyone think of a way? So the variable we're trying to find is TF. And we have it in a term where it's squared. We have it in a term where it's linear factor, and we have a constant where it's not. Quadratic formula. Yep. So whenever you have all three of those things, a constant, a linear factor, and a squared, quadratic formula is the quickest way to go. All right, so for quadratic formula, this is B, and this is C. And the formula says TF is going to be equal to negative B plus or minus square root of B squared minus 4AC all over 2A. And anybody who has a TI calculator, if you come ask me to do it sometime when I'm free at lab, I can it'll take 30 seconds to enter in a program that'll do this, and then you won't ever have to enter this in by hand. You can just start this program and enter in ABC, and it'll spit out the answers. So come do that if you want that. Yes? What? Well, in this case, it's going to be easy. Sometimes it takes sometimes it's a little more complicated than this, but in this case, we're going to have one answer that's positive and one that's negative, and we only deal with positive times, so that'll be easy. Okay, so in this case, the two answers that come out are 3.53 seconds and negative 0.086 seconds. We want the positive one. We don't want the negative one. So. And now if we go back to step 2, now we know TF. We know the acceleration. We know the initial position. We know the y component of the final position. And we know the initial velocity. And we're trying to find PFX. And so now look again to see if there's an equation that works. And this time, now that we know TF, this one will work. PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. So PFX is equal to 0 plus 36.25 times the time final we just calculated, 3.53, plus 1/2 times AX. What's AX? 0. So be careful with that. It's really easy to put in negative 9.81 for that, but remember the X and Y components of acceleration are different, and the X component is 0. So this all goes away. And the answer is just going to be 36.25 times 3.53, which is 127.96 meters.